Okay, so this brings us to the fifth part of this lecture. And in this one, I'm going to talk about the second problem, which is the decoding problem. And for this, we're going to use the Viterbi algorithm. So just a bit of a review or revision of the previous part. In the previous part, we were given the sequence and the model, and we wanted to infer the probability that this sequence was inferred from the model. And the idea was that we used to take, or if I take the example again, so all paths that are coming to this point, we need to take sum of all those paths. We need to compute probability of each path, and that probability is basically the Viterbi probability at the previous point multiplied with the probability of this path. That is the probability of this one, and you need to sum it up with the any other path. So all paths, the probability of all paths need to be calculated and summed up to find the Viterbi variable for till this point. And that was again used, since this is computed, this can be used after multiplication with this or after multiplication with this. And the major reason why the computational complexity is decreased severely is because now we are not computing the same paths again and again. For example, if you want to compute the probability of reaching at this point, you can note that there are two paths that are coming. But if you go back further, there are actually many more paths. For example, to reach here from start, I could take this straight line. I could take this line, right? I could take cold and hot and then hot. I could take cold and hot. So you can note that there are, a lot of paths that are possible. But all those paths are passing through these 2 points. If I can find probability for this one and variable for a value for this one, all I need to do is just sum these two values up to compute the probability. That was all that was required for the forward algorithm. Remember, the forward algorithm is a likelihood computation. In likelihood computation, it is sum of all paths leading to this point. So what makes decoding problem different? Well, there are two major differences. First of all, unlike forward, in this case, we don't need to take all paths, but we just need to take the maximum of all paths. So in the earlier case, it was sum of all paths, and we use the summation sign, as you can see here. So this is summation of all paths. In case of Viterbi, because now we know that this model was used to generate the data, all we need to do is which path was being followed. And the idea simply is the one that contains the maximum value is probably, so instead of summing it up, so in this case, if you noted earlier, there was this sum sign between them. There's no sum here anymore. It is max of these two values. Whichever value is maximum, we'll select that as the V variable of the corresponding state. In this case, V2, we're going to take maximum of this one. For V21, we're going to take maximum of this path and this path. So whichever is maximum will be selected. So that's the first difference. Instead of a sum sign, all we have to do is in this algorithm, we replace it with max value. The second difference, when we compare it with the forward algorithm, is that we need to keep track of which path is being followed to generate this maximum value. So for example, as you can see, the maximum of both of these 0.32 into 0.2 and of 0.02 into 0.25 is naturally, I think, 0.32 into 0.2, which is 0.064. This 0.32 is coming from this path, and you can see that we have made it more bold. We have made it more, we have highlighted this one. So to follow, to which hidden state was followed to reach this cold state in V2, the answer is that we started off in hot and then we went to cold, right? It's not cold to cold because this one has lower value as compared to this path. And it is just a comparison. So for example, for cold, what I need to do is, first let's compute value here. And actually the value here for hot and cold is exactly the same as that of the forward algorithm. And you'll note the reason for that is, since there is only one path, we just need to compute the same values. V11 or alpha 11 was 0.02. V12 or alpha 1 2 is 0.32. So these are common, and the way to compute them is exactly the same. Probability of starting in hot state multiplied by probability of observing 3 in hot state. 0.8 into 0.4 is 0.32, and similarly on this side we note the same pattern. Right, then let's move on to this point. V22 is basically, there are two paths coming. One is this path and one is this path. For this path, we have 0.32 multiplied by 0.6 multiplied by 0.2. For this path, we have 0.02 multiplied by 0.5 into 0.2. So if you have more than one path coming in, you need to take the maximum of that path, since there is only one path that leads to this. And that one path is probably 0.32 into 0.6 into 0.2 gives you a value. The other value is 0.02 into 0.5 into 0.2. So take the maximum of both of these, and the maximum of both of these is probably 0.32 into 0.12, which comes out to be 0.038, and 0.038 is the value of V22. For this value, again, need to use 0.038 multiplied by probability of moving from hot to hot multiplied by probability of observing 3 in hot. That is the cost of this path. The cost of the other path is probability of so V21, which is 0.064 multiplied by probability of moving from cold to hot, probability of hot given cold, multiplied by probability of observing 3 in hot, right? So those are the probabilities that defines this path. Then you take the maximum of both of these. Whichever is the maximum is going to be your V32. Similarly, you can calculate it for V31. And if you take finally the maximum of both of these, the one value that is maximum will be the path that is taken for the last step. So that it kind of indicates whichever has a larger value would probably be indicating which path is being taken. Note that for keeping track of the path, we need to keep a thing which we call back pointers, right? We need to keep track of which path was being followed. So you need to have back pointers continuously pointing out to the maximum value over here observed is 0.064, and that is observed by keeping a back pointer pointing towards H. The maximum value observed here is 0.038, and again it came from this H. The maximum value over here, of course, since there's one path, this one will point to start, this one will point to start, and that's the end point as well. So when computing these values, you'll compute it by actually using the same left to right formula to compute all of these values. However, instead of summing it up, you'll be using maximum. And at each point, once you compute the maximum, you'll draw these dotted circles back to the dotted lines back to the one which got selected, so that you know which path was used. Finally, you get a value here, and based on that value itself is not very important because we're not computing the probabilities. The important thing in this algorithm, in the Viterbi algorithm, is the path that is being followed. So using these blue lines, you'll again follow the path which was followed, and you can emit the corresponding states at each step. And after emitting these states, you can just reverse them to find the right order. So for example, if I had only observed 3 and 1, and let's suppose that if I compare this value 0.064 and 0.038, 0.064 is larger value. So naturally, my state from which I'm kind of starting off is cold, right? So that's the last state. 1 was generated from cold, 3 was generated from hot because of this pointer, and finally I started off in hot state, right? So my path is going to be hot and cold. To generate 3 and 1, I need to start in hot and then go to cold, and then that's end of it, right? So to generate 3, 1, I need to reverse this formula. While calculating the values, I'm going in the forward direction, but at each point I'm going to make up a back pointer, and when I'm going to use the when I'm going to calculate the path, what I need to do is I need to start again in the reverse fashion. So from end, I need to go back to start, and once I get that sequence, I need to reverse it, and that is the way this is going to give me the best possible path, the hidden path that is underlying this one. And finally, the next problem that I'm not going to discuss here is the forward-backward algorithm that is used to train the HMM and determine the HMM parameters, learn the HMM parameters. That is out of scope. For this exam, what you need to do is you need to understand that again. I mean, the simplest way for the Viterbi algorithm is one way is the brute force method. In the brute force method, what you need to do is compute all possible paths leading up to the last point. So all possible paths, you need to calculate their probability. And after you calculate the probability, you take the maximum of it for the last point. Again, that is not feasible. That is computationally impossible because the paths will grow exponentially with the growth of the observation sequence as well as with the growth in the number of the hidden states. So that becomes almost impossible. The alternate way is to use another dynamic programming algorithm, which is kind of very similar to the forward algorithm that you saw. The only difference between these two algorithms is there are two major differences. One is that you need to have a backtracking method, a back pointer. And the other difference is instead of using the sum operator, we're now going to use the max operator. So those are the differences that you need to see. The rest of it is exactly the same. The kind of questions that you can expect from this part are also going to be same. You might be asked, given a model like this, I might ask you to execute the brute force method, which is to compute all paths and then take the max of it. Or I might ask you to give you the choice of calculating the values, in which case I think you won't be in that particular scenario where I don't force a method on you. You can use Viterbi on your own, or you can use the brute force. Remember, if you use brute force, it will take you much longer. So remember to try and apply Viterbi as much as possible. If not, if the brute force is not enforced upon you in the problem statement. The second thing is that for this case, you can either select the maximum after calculating all paths, that is the brute force method, or you can actually for each of these values calculate the v variable, and from this v variable calculate the next v variable. However, remember to always include the backtracking arrow with you at each step. So whenever you calculate this, remember to add the backtracking arrow or the back pointer for your traceback. The traceback will always start from the end and go back to the start. However, once you reach the start, you need to reverse the order which you get from the backtracking. That is the final step. Okay. So I hope you kind of understand the algorithms, the different ways to calculate them. In this case, of course, this was taking the ice cream model and making it go on. I could take the ball and earn model. I can take the coin toss model, or I can take any other model, maybe simple, a dice model, or some other model with 4 states or 3 states, and just come up with the weather model, or I can come up with some biological model. The details don't matter. The only thing that matters is you need to be able to identify the elements of HMM. After identifying the elements and putting them in the right place, the next step is I'll want you to take these elements, and after picking up the elements or identifying them, put them in the proper graphical format, and from that graphical format you should be able to identify if you have to apply Viterbi algorithm or the forward algorithm. Whichever algorithm you choose, you need to draw a similar graphical representation of it. From this graphical representation, then you need to identify and calculate the values of V parameters, the Viterbi parameter, or the forward parameter, right? Which is alpha, represented by alpha. So calculate these values, and based on these values, answer the question that is being asked to you. If it's a decoding question, you need to come up with the path, the hidden path that generated these sequences. If it's a likelihood question, you need to compute the final likelihood, the likelihood probability. And this final value is what is important to evaluate the whole sequence being generated from this model, right? So that's the final thing, I think. I'll try and upload some problem statements, at least 2 to 3 different problem statements soon on the website as well, so that you kind of are aware of what kind of questions to expect in the quiz next week. But I think with the so many examples that I've given at the end of this particular part, I think you should be able to kind of get to know what needs to be done and the different parts that you probably I've divided the lecture into different parts so that it's easy for you to follow as well. If I give really long lectures of 1 hour or 2 hours, I feel that your concentration might be lost. So for that reason, I've divided the lecture into 5 different parts, and each part concentrates on one problem at a time. And I really hope that you have understood this and there are no issues with the understanding of likelihood computation or with the decoding problem, forward algorithm, brute force method for both the problems, as well as the Viterbi algorithm, the dynamic programming solutions for both of the problems. As well as, you should be able to understand the elements of HMMs and elements of Markov chains, and identify them from the statements and put them out, and also compute the different probabilities for Markov chains and for HMMs. So with that, I think that's all for the lecture that was supposed to happen on Thursday. I hope you're clear on this, and I'll try and give you some at least 2 to 3 practice questions, relevant practice questions in by tomorrow, hopefully. So best of luck for the quiz next week. We'll start with the quiz, and so be on time, and you'll be given exactly 1 hour. And in that particular case, I don't want to hear anyone submitting it late or with any other excuses. I'll close it at the time, and there will be no retake whatsoever of the quiz next week, since it's not technical, and I don't want to hear like, I'm traveling or something. If you miss the quiz, you miss the quiz. That's it, right? So thank you very much for listening to this lecture, and I hope you have understood about hidden Markov models. Next week we'll have quiz, and I might show you how to run HMMs on basically using the sklearn library and on Python. So that's what we're going to do next week. Thank you very much, and take care. Bye-bye.